Good afternoon, everybody. We're going to go ahead and talk about stoichiometry. Now, this is going to be for learning goal 2. Sorry, not 2.7. This is going to be video 2.6. Sorry, going mainly over parts of learning goal 2.04 as well as 2.07. There we go. Now, overall idea is we want to understand what is stoichiometry. How are we going to use it in terms of understanding the relationship between different chemicals when they're mixed and the compounds and reactions that will occur. So let's go ahead and jump right into it. Now, everybody loves cookies. Well, most people love cookies. Now, when I go into the kitchen, I don't just go in and start mixing things together and throw this in there, put it in a bowl and throw it in the oven, and boom, I get delicious cookies. If I could do that, then that would be a miracle. But most times, if I was to go in and do that, might cause a little bit of a problem. Things might not taste right, or they may not come out right because I may not have added the right materials. If we need more, based on a recipe, I can usually double it, triple it, and figure something out. This is going to be our recipe, our balanced equation. So if you remember video 2.5, we went through how to balance the equation. Now we're actually going to put it into action and add it with the conversions that we've been doing to figure out the overall process and see how this is all related. Now, stoichiometry, overall, is Greek for measuring elements. Defined as calculations of the quantities and the chemical reactions based on a balanced equation. In other words, how will the reaction or the amount of products, or if I'm comparing the two reactants, relate, the amounts that I'm going to get based on the balanced equation, based on my recipe. Now, we can look at the balanced equation in 4 different ways, and we'll do examples for each. We can look at it in terms of particles, moles, mass, or volume. If we look at it in terms of particles, I look at this equation, it would be the same as me saying 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to produce 2 molecules of water. Very straightforward, not too much of an issue. Now, would this help us in a lab situation? Not so much. So how do we move on a little bit past this? The second time, and this is what you'll hear me say most often, is we're going to look at it in terms of moles. This means we got to pay attention to those coefficients given to us out front. This is telling us how many moles of each compound we're actually dealing with. So looking at this equation, I have 2 moles of aluminum oxide. When it decomposes, yields 4 moles of aluminum and 3 moles of oxygen gas. Now, when we do our mole calculations, mole or gram, whatever they should be, we have to remember we're going to utilize something called a mole ratio. And this is basically what a mole ratio is. It's looking at, it's sort of like our bridge between our old substance and our new substance. You'll usually hear me say moles you want divided by moles you have. Whatever the given compound was that you had at the beginning is going to go on the bottom, so you'll be able to cancel it out. And whatever new compound you're moving into will go at the top. This will make it a lot easier, especially if we're doing like one-step conversions where it's just, moles to moles. Only one step to worry about. If we're doing grams to grams or grams to liters, anything like that, then it usually be a 3-step, but you always have to have this mole ratio involved. Now, pay attention here at the bottom of the slide. You notice that it says the numbers come from the balanced equation. So whenever you do your any type of stoichiometry, really, you have to have a balanced equation to work from, because your mole ratio is going to be dependent completely upon your balanced equation. Now, this is going to give you an idea of how things sort of flow. When I'm doing stoichiometry, if I'm given the mass of the known substance, whatever it is I'm starting with, first step is I need to convert it to moles. After I've converted to moles, now I have moles of my known substance. I need to take it a little bit further and try to figure out how to find out the information about my unknown substance. This is how I'll figure that out. This is where my mole ratio comes in. I'm going to switch between the two based on the ratio in my original recipe. Now, this will give me moles of my new compound. Most times you'll have to take it a step further, especially if we're doing a lab. You have to be able to gather the data for mass so that you can actually use the balances to figure it out. That being the case, that'll take us to our final destination. The process we're going to use overall for stoichiometry is going to be used in this unit, and you're going to see it again come up in Unit 3, so make sure that you are prepared and know what it is that you're going to be doing. Now, all of this still comes from our law of conservation of mass, which basically states, well, even though I wouldn't be able to hear you anyway, it states that mass is not created or destroyed in a chemical reaction, just rearranged. So we can check the mass by looking at the number of moles. If I have a balanced equation how I'm supposed to, I should be able to look back at it and say, okay, I have 5 grams of carbon on my reactant side. I'll also have 5 grams of carbon on my product side. If it's not true, then I have a problem and I need to fix it. So, looking at this information, I have 2 moles of hydrogen gas, plus 1 mole of oxygen gas yields 2 moles of water. 2 moles of hydrogen, do my regular mole-gram conversion like we did before, with my molar mass given to me at the top here, 2.02 rounded, and that gives me 4.04. 1 mole of oxygen gas, set up my conversion factor, 32 grams of oxygen over 1 mole, and got 32 grams. So overall, my mass on my reactant side, is 36.04. I need to make sure that I have the same thing happening on the other side as well. So let's look at the other side. 2 moles of water. Each mole of water has a mass of 18.02. So do my mole conversion, and I get 36.04 grams of water. My reactants equal my products. I know I'm following the law of conservation of mass the way I'm supposed to. Remember, it has to equal the mass of the products. Mass of reactants must equal mass of products. If it does not, we've made a mistake and we have to fix it. Now, the other way that we can look in this is in terms of volume. At STP, which is standard temperature and pressure, 1 mole of any gas occupies 22.4 liters. Don't stress over this. We'll come back to this a little bit later when we go through our gases unit, so don't stress over it. Now, still looking at it in terms of moles, the things that you want to know, and this is just a little thing to keep in mind, mass and atoms are always conserved, meaning when we deal with atoms and mass from both sides, from reactants and product side, they'll always equal out. But things like formula units, molecules, moles, volumes, they're not necessarily going to be the same on both sides. And we'll explain that a little bit later as we continue to go through. Now, here's a practice problem. Take a moment, pause the video right here, and I want you to actually solve this. Show that the following equation follows the law of conservation of mass. Show the atoms balance and the mass on both sides are equal. Go ahead and pause right here, and I'll come back in just a second. Did you really pause? I hope you did. Now, let's go ahead and go through it. All right, so here's my balanced equation. Oops, did I miss something? No, we're good. Okay, my balanced equation in terms of each time we use 2 moles of aluminum oxide, we're going to make 3 moles of oxygen. This is given to us by our mole ratio, or I'm setting up as my mole ratio. So 2 moles of aluminum oxide over 3 moles of oxygen gas, or another way that I can set it up is 3 moles of oxygen gas over 2 moles of aluminum oxide. Both ways, it still equals out to be the same truth based on our balanced equation. Now, here we go. How many moles of oxygen are produced when 3.34 moles of aluminum oxide decompose? Have my balanced equation before I start, so that's good. In this, it tells me it's a mole to mole conversion, moles of oxygen from 3.34 moles of aluminum oxide. So I need to go ahead and get started. So here's my table, and I write my given information the same place I usually do. 3.34 moles Al2O3. And sorry, I ran out of space there. Please forgive me. Now, since I'm going from moles to moles, I only need a mole ratio. Since aluminum oxide is what I had on the top, I need to put it on the bottom so I can get rid of it. According to my equation, 2 moles of Al2O, or O3 is what I usually put in to get out 3 moles of O2. Because it only asked me to go from moles to moles, once I cancel out these units, I realize I'm where I'm supposed to be. It's just a matter of me now plugging it in. So let's go ahead and clear the ink and see if we match up. 3.34 moles. Our conversion factor, 3 moles of O2 over 2 moles of Al2O3. And multiply by the top, divide by the bottom, we come out with 5.01 moles of O2. Now, as long as we have our balanced equation, if we have at least one of the numbers, one of the values, or a value for any of our compounds, we can figure out how all the other ones are related and how their values will change based upon that single compound. Here's a practice problem for you to go through. And this one is, again, another moles to moles. 3.84 moles of, this is ethine, sorry, are burned. How many moles of O2 are needed? So now, instead of comparing reactant to product, we're comparing reactant to reactant. So let's look at it. 3.84 moles of C2H2. Make my table. Oops, sorry, it droops a little bit. And we have another mole ratio. So we have 2 moles C2H2 and 5 moles of O2. My units here cancel. 3.84. I'm going to go ahead and plug this into my calculator. 3.84 times 5 divided by 2 gives me 9.6 moles of O2. So, straightforward, we're going to do the same type of thing as we continue on. And don't worry, I will be posting more videos for this. More problems. So, how do we get good at this? With stoichiometry, as with anything else, you have to practice. If you don't practice, it won't come to you. So, as you work through the problems, and I can always get you extra, there's never a problem with that. Make sure to see me so we can make sure you understand what's going on. So, what are our steps again, just to review? Correctly balance the equation, number 1. Convert the given amount into moles. Set up the mole ratio to convert it to moles of the new compound. Convert back to unit that we want, grams, liters, particles, whatever the situation may be. Now, this is one example, and I'll just do this last one and then we'll be ready to go. This is one where we're going from mass to mass. You're given, just like before, we have 6.50 grams of aluminum is going to react with an excess of oxygen. When it says excess of oxygen, it just means you don't have to worry about how much oxygen is there. And the question is, how many grams of aluminum oxide are going to be formed? Now, since I'm starting off with grams here, that means grams has to come to the bottom. Since it's just aluminum, that means I'm dealing with 26.98 grams pulled from my periodic table. And you notice that I'm loading it with my units. Oops, everything just sliding down. So, to continue on, my next step is my mole ratio. Since I have moles of aluminum, 4 moles of aluminum is what I put in to get 2 moles of aluminum oxide out. There we go. Now, last but not least, 1 mole aluminum oxide. And I need a molar mass for that, which is going to be 26.98 times 2 plus 48 gives me 101.96 grams Al2O3. Now it's just a matter of multiplying and dividing. And this is where we're going to cut it off here. You can go ahead and finish this last part up on your own. I can't wait to see you in class. Make sure you bring any questions that you have so that we can make sure you're taken care of. Have a great evening and look forward to seeing you.